All right, let's do it again. So, we are going to talk about Mandelbrot's ideas today for the rich gets richer story. That's very exciting. Mandelbrot, which means almond bread, and that's what he would tell you in person. Pretty feisty character, Mandelbrot, quite famous for telling other people that they're not very smart, basically, in various ways. So, worked at IBM for a long time, at the Watson lab. Anyway, so lots of things, all sorts of stuff. Finance, he worked on finance. He sort of found the fractal structure there and coined the term fractal, of course. He's famous for that. But this is work, some of this work's pretty old, right? The Simon work is 1955, Mandelbrot is 1953. So we'll see them have a little bit of they go head to head via letters in journals, which is kind of fun. All right, Herbert Simon. So let me mention another thing about him. So Google Scholar, you have to set up your own account, right? You can kind of search for people, but if they haven't set up an account, it's not very well done. But a few famous people have been their pages have been put together. Feynman's up there, for example, and so on. Anyway, this is a lot of citations, right? I mean, there are more on Google Scholar in general than, say, Web of Science, but 260,000, of which, and this is the way, science grows in this ridiculous exponential way, close to 80,000 in the last 5 years. So he's going to go to 1 million, which is bananas. And, these are huge numbers. All of these things are huge, right? If you get one citation, your paper exists, right? That's not bad. That's pretty good. The modal number, because the power law size distribution, of course, right, for the number of citations. So it's this heavy-tailed thing. I can't remember if it's 0 or 1 is the mode, right? It's probably 0. It should be 0 given the things that get published. But it should. So most papers get 0 or 1 citations, and then after that, if you get to 10, Google will. This is what this funny little upside-down thing here, 10 index is how many papers got cited at least 10 times. And that's like, well done, that's good. So we'll make an index for that. And then maybe some of you know about the H index, which is named after a person who invented it, which actually is not, okay, that's unusual. So 161 citation, H index is 161. So that means 161 papers that have at least 161 citations. And getting to 100 for a paper means something. It really exists. It's out of your control by that point. People are actually citing your paper. And it's probably a lot of the citations, because this is a rich gets richer, a lot of them will be, things like networks are interesting, 1 through 20. You're just in there, So the famous papers just get cited a ton of times like that. But these are huge numbers. 10 is a big deal, 100 is a big deal, 10,000, you've changed, you've basically set up a field at that point. So anyway, you can look around at other people's pages. There's something we'll talk about later on with networks. So there's a problem for us as humans and lobsters or anything that lives in some sort of social network, is that your friends are better than you on average, which is really disappointing, right? And that's sort of the first basic thing, is that they have more friends than you, which is really disappointing, right? So there's that. They also have more citations than you. So it's an interesting, and it could be, wealth might work like that as well. And it depends on the data sets and so on. But basically, that seems to be a general thing. That sort of an inequality upwards is built into structure, which is pretty interesting. So maybe you have a bootstrapping of keeping up with the Joneses, sort of built into just the way networks are. All right. Anyway, so this one, he's kind of at the top of the hill, though. This, right, Herbert Simon looking at other people will be, they've done okay. Anyway, I mean, 1,000 papers is just, I don't know how that happens. Anyway, I sort of do, but it's crazy. Okay, so there's that. What else we got? That's something for networks later on. Yes, okay. So let's see how we go. We may talk about some extra things at the end, but basically I want to talk about the rich gets richer thing in terms of optimization. All right, so we had Simon's model, all right, this stuff. And then we're going to talk about optimization, which will be an entropy story, right? So we have to measure information in some way. We have to measure cost in some way, and we'll see how Mandelbrot set this up. This is purely for language, right? There'll be no sense of what a city could do in this story, or genus, or with species. You could try to think about how that might work, but it's really geared to language. Okay, what else have I got to show you? Okay, yeah, here's a little thing. I know, I spend hours doing these things. Okay, so, right, this picture. Nope, that's the wrong one. We're in the wrong place. Here, optimization. This one, okay. The dream of efficient language. So we'll see some sort of statements about evolution and language and so on later on. But there are some really extraordinary patterns for the evolution of language. So it's kind of clear now we have enough data that there really is some sort of drive in certain ways to clean things up. It's code, right? So we kind of make the code a little better. All right, Mandelbrot. So it's, so he came up with the term fractal and everyone got excited. It was a lot of fun for pure mathematicians and mathematicians in general because they got to make beautiful pictures and lure people into the cult, saying, look at the pictures we have, come work with us. We don't understand, we can make them. We don't have physical mechanisms really necessarily. I mean, there are little mathematical games that produce these things, right? So the physicists are always been like, well, that's great, but why? But we've got there in certain places. We're full of them. Fractals are inside us, right? We've got a tennis court for lungs sitting in here, and that's all wrapped up in a little, ball. Anyway, right, fractals everywhere. Blood networks and blah, blah, blah. Okay, good. So, Mandelbrot. So Mandelbrot, passed away, a few years ago, and it's sort of part of teaching this course was at some point I had to say that he's no longer around. Real character. Okay, so it's going to be an optimization story. Very, it's kind of an appealing idea, right? Language is efficient. Some people get very carried away with evolution and producing the best things. Of course, we use it in computer science, right? Evolutionary computation gets us the best thing or something that works. Of course, it also gets us the platypus, so it's difficult. It's an excellent animal. Let's see. So, very simple idea, and this sort of fits in with the Zipf story, right? Which is to communicate as much as you can with as little cost. So we have to measure those things. You're getting information across. You've got basically, when you talk to someone or you write a story and then they read it, you've got a little bit of code in your head and you're trying to get that code to run in their head, right? If it's propaganda, it does a certain thing in their head. If it's marketing, it attempts to do a certain thing in their head. Okay. That's your job when you write a little story. Okay, so we're going to have measures of these things. So H is the standard kind of thing for information. So this is Shannon's information. I'll give you a simple way of thinking about how we can compute that. It's unfortunate, the term, in a way. I don't know if I say this again, but information, it feels like meaning, right? It sounds like meaning, yeah? So that's not true. Let me see if I can absurdly find Shannon's first paper. Others, maybe 1949. Yeah. So this is Shannon's paper. This is the first one. It might not be in... Yeah, so he's talking about frequently messages have meaning, and he's saying, well, basically we're not going to do that. We're going to measure information, and that's going to be a different thing. Not such a good thing to show. But let's get this again. And apparently, von Neumann said you should call it entropy, and it does look like entropy that you get in statistical mechanics and so on. And the joke apparently was that he said no one understands that, so you'll be fine, right? But information elicits the wrong kind of thing in most people's heads. It feels like you're measuring the meaningful content of something, and that is crazily hard. Okay. All right. So, language evolves, right? We start with the ook thing, and then we add lots of words, and then we trim it down, and it changes, and it's very interesting how language changes over time. Verbs, for example, have regularized. Maybe we'll show you this later on. Verbs have regularized, and it seems they have a half-life dependent on their frequency of usage. So verbs that are used very infrequently tend to, if they weren't regular, they tend to become regular quickly. And the rate is something like 1 over frequency to the half. So you could estimate from that we'll end up with to be and to have, the most common verbs in English, being regularized in about 40,000 years. I be, you be, she be, he be, we be, right? I mean, it really hurts for someone to say irregular verbs in the wrong way to you, right? Kids will do it all the time because why would you do, I've found these rules, I'm a kid, I found these rules, the plural thing, I'm one of the childs in here, so why are we doing this? And you're like, well, that's terrible, you can't say that. But these rules tend to win, and it's kind of a code thing. They tend to win, right? So we have some German stuff floating around. I mean, lots of German, lots of French. There's all sorts of crazy stuff in English. En is a plural, right? It's a German thing. But the S business has worked out. We kind of float around with the I now and then, because that sounds good, cacti and octopi. But octopus is a Greek word, so it should be octopodes. So it's just, anyway. And octopuses sounds fun to say, so you should say it. So you can see something like Google Ngrams, which is somewhat, you can see certain things winning over time. All right. Past tense is a good one, like snuck. Snuck. You snuck into the place. Snuck is doing well because it's such a good word, right? There's sneaked, which is also good, but snuck is pretty great. Okay, all right. Just saying that there's a lot of evolutionary stuff, and you can see it from Old English to Middle English and so on. That's just English. All right. So we could maximize this, the amount of information divided by the cost, if we can measure these things. Well, so it's going to be some extremal sort of thing. There's going to be perhaps derivatives, setting them to 0, that kind of business, right? Okay, but it's going to be a little bit more than that. We can minimize C over H, right? Okay, so we have to set those things up, and this was the game. It's quite clever what Mandelbrot did. Okay, so this is a big deal. Optimization is going on. How much of it is working away? Can these things really get tested out, and so on? It doesn't work so well for robustness, right? It's good to have redundancy. You don't want to have something that's super lean and so on. Yeah. I mean, Volkswagen, right, just did some bad things, and apparently their structure, we could talk about organizations, I do in the next course, is pretty hierarchical, right? The sort of the idea of what military structures are, which is not true, right? So there's a lot of cross ties in organizations that are very successful, and some of them structure it that way. So anyway, this is, that's an example of kind of what looks like kind of, being overbuilt and so on, right? Okay, right, big problem. Okay, so let's have Mandelbrot versus Simon to start with. So we'll get into Mandelbrot's thing, but let's go through this little back and forth. It's kind of fun. So I'm going to give it this theme. You should. It's terrible film from the 80s, but very famous. So you'll see Colbert actually, the old Colbert Report would have a couple of these, and so he would absorb the audience from other pundits when they left. I think Keith Olbermann, left MSNBC, and he tried to absorb the audience, and then it didn't work, actually. Yeah, right. Okay. The ridiculous story here, right, is that there are these immortals, and they have to basically kill each other with swords, and the last one left gets some sort of prize, which is to keep living, basically. But anyway. But then they made so there should be only one of them, because they made another film, and then they made a third film, and they made a TV series, and then this horrible backstory where they're aliens and stuff. Oh, it's fantastic. So they have a Frenchman playing a Scot. That's important. And then they have Sean Connery, who's Scottish, playing a Spaniard. It's just fantastic. Just fantastic. All right, Highlander. There can be only one. That's the story. All right. And it has Queen. Queen is fantastic. Really good. Queen, right? Freddie Mercury. Great music. All right. Okay. Very good. So The Quickening, that's what it's called. Let's see. So there's the trailer. I won't play that. That's too much. So here we have Mandelbrot and Simon. Not the best photos, I guess. But this is this sort of sequence of papers, right? So they have their Mandelbrot. So Zipf is 1949. It's published, and people are like, oh, this is the thing now. Yeah. People have been sort of getting at it a little bit, but then Zipf's big book comes out, and they're like, okay, let's figure it out. So, strong title, Informational Theory of the Statistical Structure of Languages. Okay, good, good. And that's what we're going to talk about. And then we have this terrible thing from Simon, which is a great paper, but a terrible title, of the impenetrable exposition. And then, this is, this is 4 years later, right? This is not the tweet scale. This is 4 years later, a note on a class of skew distribution functions. And he's going to call the name out by that Simon guy, right? And Simon, this is a year later, some further notes on a class of skew distribution functions. I'm just going to talk about my stuff, right? I'm not going to go ad hominem. So that's 2. And then we have this one, final note, on a class of skew distribution functions, colon, analysis and critique of this guy. I don't know if they ever met. Reply to final note by Mandelbrot. And then postscriptum to final note. Now they're having a great time. This is happening quickly. These are letters they're publishing quickly. And then reply to his postscriptum. It's like that. Now he's going to say that guy who keeps talking. Yeah. Anyway. Yeah. Pretty good. So, a couple of lines from them. And this is one of the examples where they call it some crazy things. So this is Mandelbrot. We're going to say what we said before. We're still right. The Pareto-Yule Zipf distribution. Our objections are quite valid and blah, blah, blah. So Simon, you're an idiot. You're basically an idiot. Yeah. Mandelbrot has proposed a new set of objections. Like his earlier objections, these are invalid. So it's just full of this sort of stuff. And I guess not really resolved. And I'm sure they both thought they were right to the end. And we'll see that Simon seems to be basically right, although the form that we end up for language distributions, for word distributions, does seem to be sort of match up to an optimal story anyway. So it's kind of for free you get it, which is interesting. Okay, then I think there's some silliness here. Plankton, yeah, right, that sort of thing. Okay. Right. Okay. One of the great evil geniuses of fiction. Okay, all right. This is I'll just show you the start of it. This is a documentary from Australia. But this is another way of framing this. You're familiar with this? I can tell you. Mad Max, right? Now there have been 4 of these in this ongoing documentary of life. Just bad, just dead. Anyway, yeah, you know what happens. So they're chanting, one man, yeah. So 2 theories enter, 1 theory leaves. All right, okay, fine. So we could do that too. Yeah. I know. Well, you want to give academics a little more, yeah. Actually, they are kind of violent people. What's that? Yeah, so we can look at this. Yeah, so they become letters. Which needs less review. So 19, 24, 25. So so there's information and control was the journal, and you can see they're not right in order, are they? And this one is so it's information and control was the journal. We got all 17, 19. Yeah. Yep, back and forth. Yep. There you go. So they found themselves a venue to have this out. Yeah. Yeah. There's some great stuff like this. There's one that if we get to it later on, which the title of one paper is "The Theory of X, Y, and Z is Mathematically Incorrect and Biologically Irrelevant." Right? And they got a right to reply. So their title is... no, actually, they wrote as a question. That was the mistake. They wrote as a question, said, is the theory of X, Y, and Z mathematical, right? And then the title of the reply is, yes, it is mathematically correct and biologically relevant. So they shouldn't have done that. Yeah, that was, yeah. Okay, good. Yeah, but I guess now it will be, tweets. Violent tweets. I was going to sort of frame them as tweets, right? You can get those little, all right. Or just messages back and forth. You're an idiot. Okay. All right, so some abuse back and forth. Documentaries. Okay, so let's see if we can work it out. All right. I'll sort of give you a simple-minded way of thinking about measuring information, but it is a spectacular thing, quite powerful. But people do use it in a bit of a bit of a way to sell things that's a bit too much, probably sometimes. We've measured the information content of this, and it's greater than this, so you kind of get the idea that this one is smarter than the other one, maybe. But the thing that has the highest information content for a signal is random noise, right? So it's not a good. So it's a very tempting measure to say, oh, let's use this for complexity. It's no good at all. But just complete gibberish, that's maximum information. Because what it's about is how much effort would it take to encode this, and you need a lot to encode that because you're not sure what's going to come next. You're uncertain. So the better term for this is entropy, or uncertainty is another term as well. But the better term is entropy, because then we're not going to we're going to say, I don't know what that is. Okay. Everyone uses information. So actually, there's a beautiful spectrum of information measures, and there's some in ecology, for example, Simpson's measure, and so on. Which there's generalized entropy, very nicely. But there's something very special about Shannon's. Anyway, so we'll get to that. All right, so let's imagine we have this language. It's got n words. Right, he's going to make some pretty severe assumptions. And eventually we'll see monkeys involved, which is strange. It's not his fault. So you're looking at it streaming in, and you're counting how many times words appear. And we know just in the real world that we have this very skewed distribution. But let's say we have no idea. We're just measuring. We get some frequency of the word "the" and the word "platypus" and Garfunkel. Right, so those words have some frequency. We normalize it, and after a while, we start to say, this is the probability of getting a particular word. So it does assume that it's all jumbled, right? It's not structured. It's not 4% of all these words are the, and then they're not ordered. It does assume sort of structurelessness after that. Funny word. Okay, random, right? It's obviously not true. So this is an interesting piece. It really will matter that words are made out of letters for this theory, and that's not true of all languages, as we know. So, but that's fine. So we'll say the alphabet contains m letters, so we'll have generalized alphabets, and then here's the big assumption that you can see this isn't quite right, but maybe roughly okay. The words are going to be ordered by length, so the most common word will be the shortest word, and very oddly, if m is 26, we're going to have 26 words of length 1. And then we have 26 times 26 words, 26 right, subtracting off the doubles for words of length 2. So that's, a bit silly. All right, fine. So the word cost is going to be a length of a word plus a space. That's kind of your cost. It's going to relate to how much effort there is to write it or to say it. I guess auto-completion, I don't know what that does. Okay. Or people finishing your sentences for you. So anyway, all right, fine. Word length was certainly irrelevant over here, right, for Simon's model. Real words don't work like this. There could be some subset of them, but fine. Maybe it's roughly true, right? There's some fraction of words that work like that and some fraction. There's more work on that later that's been done later, and I'm not going to include that here, but we're just going to go through his story. Okay. Words can certainly be encoded this way, right? So if you want to encode words, you can do this. You put "the" as the minimal thing, right? So if you're doing that, if you're encrypting something, you will actually do this. And encoding schemes basically do this. And then we get back to this fighting with each other. All right. Okay. Anyway, it's a nice bit of thinking by Mandelbrot. It's good. So let's think about just a simple thing. Let's imagine we have a binary alphabet. And so ones and zeros are going to encode everything. And we're going to send them off. The Morse code's quite clever. Morse was not a scientist, I don't think. Morse was just sort of running around, I think, in Africa thinking, it'd be good if I could send some signals. I think. Might have been some poet or something. Anyway, so it's a funny story for Morse, which I only have vague sense of right now. Okay, so these are our words. They're terrible words. Yep. And we imagine there's a space as well, a space symbol, which is really a third character. So the length of these, as you can see, 1, 2, 2, 3, 3, right, out to 4. And so these things are growing logarithmically and slowly, right? The lengths are growing slowly. Yeah. Yeah, so you have 2 of length 2, you have 4 of length 3, you have 8 of length 4. Can I double things properly? 16 of length 5. And so if we did, we can think about log 2 of I. This is the ordering of the index of the word. 1 plus log 2 of I works pretty well, right? So it's going to work perfectly when we're at multiples of powers of 2, right? So log base 2 of 8 is 3 plus 1 is 4. So that's exactly the right length. These things are they're a bit wrong. You have to sort of think about why this is going to work. These are a bit wrong, but roughly in the ballpark. So we could use this as our sort of estimate of length based on its index. So we're going to order our words, and then we'll use this as a cheap way to measure right? I mean, they're repeated, and we could do all that. All right? Disgusting, or?
You could make it. You could just, if you wanted to get really upset about it, you could just say that length is log of floor.
You could do a floor. That's right. Yeah. So as soon as you do those things, you can't differentiate things very nicely and stuff. So, yeah. Yep. So horrible fudge. Yeah. Which will let us do some calculus. But it's not bad. It's not too bad. So the word length is the 2kth word, right out here, k plus 1. And so we can write that as 1 plus log 2 of 2 to the k, right? Log 2 of 2 to the k is k, log 2 of 2 is 1. So that's a way of sort of bringing the log back in there. And this connects, this is the 2k here, right? 2 to the power of k, right? That's the index. So more generally, the ith word is roughly 1 plus log 2i. So we're just replacing this with I. Okay? A little sneaky. Whoops, sorry. And if we have m letters, instead of 2 letters, it's going to be 1 plus log m of I. Right, we're going to have to count up through all these things. So it's roughly okay. But of course, yeah, as we said, we've got A, B, C, D up through Z, or Z. Z rhymes, that's better. So distinct words, and then, so how many, it's about 100 words, depends which dictionary in Scrabble, right? It's about 100 2-letter words in English exist. Depends who's been messing with the dictionary. Whether you can have ZA for za for pizza, which is good because you just crush it with that. X has always been, you got Xi and Ox and X and all those things. Q is a Vietnamese monetary unit, I think. So yeah, all right. Okay, but it's about 100. Okay, good. So that's the plan. So that's our cost, and it's got a log in it, so we kind of like that. That's good. And we can take this 1 away. That's not a big deal. It's basically this. Yeah. All right. So let's do some other pieces. So here's our cost. Good. That's the cost of the ith word. If we add a space, right, we could put a +1 in here because it's slightly longer. Fine. That's actually an important little detail in this analysis. It's a sneaky thing. That +1 matters. And we could subtract off this sort of this fixed bit that's independent of I. It's just this 1 at the start. So roughly, we've got this, right? Just subtract off the same value for each one. Point of this, right? We're going to have this at some point. I'll give you another 15 minutes and then we'll give you a reason to live for another 15 minutes. All right. I'm walking around Trader Joe's thinking, what can I? Okay. All right. So, okay, good. And logs are funny, crazy little beasts. Yeah. So we can write log m of something. Blob is, you can write this conversion. We can think about this later. It's log e m on the bottom, log e on the top. But basically log of any 2 bases, right? Log base whatever of x, log base of something else. There's just a constant of proportionality between them, which is groovy. So we can even do that. We'll say, well, the total cost then, we'll use natural log. Natural log is awesome. Good. We like to differentiate that thing, so we won't have all these problems. So now we're going to say our cost is just proportional to natural log of I plus 1. All right, good. So the total cost for our whole sort of world of things here, we've got all these words coming in, they have some probability. So that's the weighting factor, and that's our cost. Will be the sum over all the words, the probability of each word, and then this ridiculous cost thing we made up, or Mandelbrot made up. All right, so we get pi log, natural log of I plus 1. Yep, so we got rid of the offset one. The plus 1 is for a space, basically, okay. And so what later on we'll generalize this to put a plus a here because that might help with trying to tune the parameter. So remember a very fundamental thing that Simon got out was the innovation rate connected to the exponent of the power law distribution. Fantastic, right? You can measure the innovation rate. It's like measuring viscosity or something like that. It's a fundamental aspect of the system. So we don't quite have that here. This is just sort of, it gets there. This is an equilibrium kind of story. It gets to this optimal state, and that's where it is. Not sure what you do with adding words. Of course, we do add words, right? Okay. So that's cost. Yes?
I have a question about that because so when people say things like, optimization means we get to an equilibrium and stay there, and then what do we do about adding words? I think a lot of people seem to, I don't know. So when you're optimizing something, you're not necessarily optimizing something over all of space and all possible states everywhere. You're saying, if everybody just left us alone, this is the equilibrium we would get to eventually. If we didn't add any new words, if we didn't, you have these random shocks, and if you want them, maybe you can model them that way. If you want to model them as random shocks, I'm sure you can.
Well, so there are systems where you have an equilibrium points, fixed points that you can't get to.
Yeah.
And that's really the big deal eventually, right? So you sort out, here's a good description, everyone agrees. You find the equilibrium points and you're like, okay, like Nash, right? And you're okay, good, we've got this thing. And then the question is, are they dynamically accessible?
Yeah.
And that's not, that's a lot more machinery involved to get to that. But yeah. Okay. Yeah, sure. But just sort of, I'm just throwing those things onto the side just to worry about them. Maybe I shouldn't. Right, so I said this, von Neumann suggested entropy. So let's look at this thing, information content. It's a very famous measure. And Shannon was working for Bell Labs, I think, and they've got all this data thing happening for them, and they're trying to transmit signals. And Turing had just done that whole thing with the Enigma project. People are sending information around the world in funny ways. Let's see, so entropy, very famous. Right, so it's minus the probability of the ith word log base 2 of the probability of the ith word. So it's a nice looking thing. And if you think about what we just had for cost, it looked very much like this. It was a positive, proportional to it, but it was 1 plus I, just 1 plus I. We kind of concocted that. It was about its length. All right, so where does this come from? And there are various ways to get to this, but I'll just roughly say it. So it's bits. We're talking about bits now. We're going to take this language and all these words and encode them into little bit stream, zeros and ones. So this thing is so it's an average, right? If you look at this, here's a distribution. It's averaging this quantity. And what's that thing? It's always written like this, but it sort of clouds things a little. I equals 1 to n, pi, ln, well, let's do log 2, pi. And so this is pi, and there's a so we can put the minus sign in here, minus log pi, and then you can put the minus sign up here, right? Minus 1. So it's really log 2, 1 over pi. So it's the average of this quantity, right? It's a nice probability distribution. If we wanted to average, right? So if we wanted to average I, right? The average value of I is the sum of I pi, like this. We've just done some of this in here. That sort of thing. This is the average of this thing, whatever it is, 1 over pi. Right? For some reason we want to average it. So we're averaging. This is the average per word of that quantity. And what is that quantity? So we're going to say, I'll explain, it's the number of bits needed to encode each word in an optimal kind of way. So you need to know everything about this language. And let's say we have a word that appears half the time. So you don't want to use a lot of bits for that. You just want to say that's 1, right? And then if it's not that word, your next thing starts with a 0. So that just immediately distinguishes those two camps, right? So if you've got a word that appears half the time, it's very structured. That means it, in fact, has kind of low information because you expect half the time to get platypus, right? So very strange text, but half the time you get platypus, right? So you could assign, for example, just a 1 to platypus. And then the other ones will have 0 something else. So I've written this down. So we can think of this as the minimum number of bits needed to distinguish these two cases. So here's the example I just mentioned. So if we've got a word that appears half the time, let's take this log 2 of 1 over pi. So we flip up a half, we get log 2 of 2, it's 1. So you need 1 bit. 1 bit can tell you. So if I come in and say the first part of this next word is 1, then immediately you say, oh, platypus, right? You have a little pointer, you have a little table over here, and it just goes platypus, right? And if it starts with a 0, you go to the other part of the table, and that's got other things. Okay. All right, so important information. Let's see. And if platypus tragically only occurred 1/64th of the time, 2 to the power of 64 is 2 to the power of 6, right? 2 to the power of 6. So this will be here. Yeah, it's here. All right, so log 2 of 64 is 6. So you need 6 bits. You need to see 6 bits before you're like, oh, that's that word, right? You know, it could be 0, 0, 0, 0, 0, 1. You're off in that direction. And this is if we do it efficiently. You could do it terribly, right? So this is a kind of a best case thing. So it doesn't talk about the encoding process. It just says that if you had all the information, you had a little bit of time in your hands, there's also, there's this, you've got to get all not the information, the words have to come by and you see them all and you have to count up their frequencies and say, okay, now I could encode it in this way. And this is the information content or the average information content of each word in this signal. Okay? There's a lot more we can do about with information theory, but that's just sort of a little thing to show you something about it. All right. So we can simplify it. Again, with this changing of bases, we had log 2. So we can always do this. We can divide by, if we want to get to log whatever it is, in this case log e, then we divide by, we just rewrite it as this, and it's log e2 is the factor on the bottom. It's just a constant. So we're into this sort of similar game, right? So there's some constant here, this blob, pi log pi, natural log. Right, so h is proportional to this. If we just put, logs are funny little things, but this is, natural log, we can use the natural log, and then we say this is constant proportionality. That's good if we want to differentiate things. Sure, you can differentiate log 2, but you have to do this anyway, yeah? Okay. All right, so that's our measure of information. It looks somewhat like the cost one, and now we're going to put them together, and the way we're following Mandelbrot's way, the way we framed it was to, we want to minimize cost divided by h, c divided by h, right? And there's our best language.
Is there a bound to the max? Because I know the reason we usually do a min is because max is not guaranteed to be bounded, where min and these sort of pretty much guaranteed to be bounded.
In this case, so in this case, I don't think it matters. I think it's just the way it's laid out, right? Because you always get, it doesn't matter because you get, they're non-zero. They're both positive terms. This is a, in some ways, this is sort of a terrible thing to do. It's mathematically totally correct to write minus, it is minus log pi, and that's nicer. But it's really, it's really this, and this is really a positive number. Because 1 divided by probability is always 1 or less. If it's 1, this is log of, so if it's 1, that means you're just getting platypus, 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 platypus. which is okay, but it gets a little tedious, right? And you also know what the next word will be. There's going to be platypus. And you're like, okay, great. So the information content of that is 0, which is a little rough because it's got platypus in it. But it's 0. I mean, technically, the entropy of that thing is 0. And it's equivalent to having a frozen state. So the statistical mechanical version would be a magnet or ice or something like that. It's frozen. And here's the story, is that the microstructure of ice, let's say, or a magnet that's fully pointing in one direction, doesn't vary much, right? So if it's sort of temperature 0 kind of thing, there's only one way for everything to line up. So there's only one microstate that corresponds to the macrostate. That's the big deal. And there are many microstates that correspond to the macrostate where we sort of experience with the air here now. Right? I can just turn, I can do it, but you could turn this little pocket of air around, feels the same, right? You could relocate all sorts of atoms and molecules and things, feels totally the same. But you can't do that once things become frozen. To use the metaphor, technically, literally and figuratively, I guess. And that's what this is like. If you just have platypus, 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 you have this kind of frozen thing, and there's no way to jumble it up and get something else. And that's why randomness is high information. Okay. All right. We doing all right? Set up. You guys going to solve some problems with this? I know the assignments are kind of behind the lecture, but that's all right because you get to come back and enjoy them. All right. Okay. Fun times. We're going to minimize this function, which has n variables, p1, p2, pn. That's the probability of all of these words. Yeah. And we know that the words are in increasing order of length. That's one thing we've said. And the thing we're going to minimize is the cost, the total cost of it's the average cost per word, and then the average information content of each word. We're going to do that. And then subject to this constraint, which is simply that the probabilities have to add up to 1. It's a constraint, which puts us in what's the thing, what do we roll out? We pull something else out of actually kind of out of your back pocket more. You've got L'Hopital and those guys in here. There is a technique from calculus, Lagrange multipliers. You pull out Lagrange, you wheel them out. They're on a cart, actually. You wheel them out, yeah. In more advanced civilizations, you push a button and they fall out of the ceiling. But anyway, okay. So Lagrange multipliers. So, but we'll say that in a second. So that's fun. That's super fun. Really nice. It will work. It's kind of amazing how this works out, actually. But you'll get to calculate that. So shorter words are cheaper. Okay, that's good. They're cheap. But longer words have more information, right? Because we've constructed this language to do that. They're rarer, so when they appear, you sort of okay, that means more, right? You can double up these and take them away and so on. No one really notices. Yeah, there's not a lot of information in them. All right. Okay, so yes, the optimization structure is this. Very nice. Okay, Lagrange multipliers, which you will become apprised with. It's really not as, it always looks bad, but it's not that bad. So you make a giant function, which is the function you're trying to minimize, plus the function that expresses the constraint, right? So here's the horrible business. Looks pretty scary. So the cost function is on top, right? Pi log I plus 1. And the information measure is on the bottom. So if you keep these things under control, you do a nice job with it, you'll be okay. And we always express the constraint function as something that has to equal 0, but we'll write it as, so we can write it as the sum of the probabilities minus 1. Yeah. Yes. Yes. Yeah, and so Lagrange multipliers, right? There's some constraint. Let's say this is your constraint. This is g equals 0. You live on this thing and you're trying to run around on it. So there's some surface under here. You're running around on this surface, and these are the directions of these are contours, so these are directions of steepest descent. And the idea is that when you're at the lowest point on this surface, as long as while you're still in this constraint. So you're only allowed to run around here. So you're running around here, you're doing a Spartan race, and you're carrying large sacks of grain for no reason, apparently. And then, and you paid someone for that. And then, so you're running around here. It really doesn't make any sense, does it? And then, I mean, you literally pay someone. Anyway, all right, so you get a medal. Okay, and possibly a trip to, ambulance. Okay. If I did that, I'd be just straight into the ambulance. Just like, I'll break my leg, I'll go into the ambulance. Okay, so save everyone a lot of time. No helicopters. Okay, so, sorry. So, you're running around on here, and the idea is that the normal to the constraint, right? If you look at the sort of 90 degrees to the constraint, will match up with the normal to the contour only at these points. So this is it. This is the point you want to find. This is the highest point. It's when you want to die, and then you're rolling down here with your bag of sand, and then this is the lowest point. So that's the idea. It's a bit cryptically put together. And I know have I been? Okay. It's actually in here. You're trying to optimize this thing, so you want the normal for this thing to match up with the normal of this thing. It's proportional to it, as long as they are pointing in the same direction. Lagrange multiplier. Lagrange. Okay. You can do it. It's totally doable. It's all set up. Totally doable. A good thing to do with this, to keep things under control, and I know it's a little distance off, but is to, let's do one little thing. So let's say we're going to differentiate C del by del pi, just the ith one, we'll do j, the jth one of C over h, for example. So it's just a little bit of help for you. C over h, well, you can write all of this stuff out, but it's a bit easier to do things separately. So dc, we'll do the partial derivative with respect to pj first. That's divided by h. Think of this as a product, right? The product rule, the quotient rule, whatever. Good for you, quotient rule. And then this would be minus h squared, and then del h using the chain rule thing, del pj. So you have to use the evil calculus thing here. I'm sorry about that. Matrixology fans. It's not, it's tough. Okay, so, no, it's all right. Okay, so this would be a cleaner way, and you just keep this as h. You keep this as h squared, and you keep this as c, rather than writing out all these horrible sums. So del c, del pj. Let's think about that. That's we're differentiating with respect to the jth probability, so they're all variables. And what is this thing? It's a sum from I equals 1 to n. Cost is pi ln of I plus 1. All of that, blob. So what's that derivative? So this could be j is 7, for example, and these guys are p1, p2, p3, p4 up to p74. Right, the only one that gets it is that one, right? So we end up with just where this matches. So we end up with just del p, del j, the words, and then it will be just p, j, ln of j plus I, j plus 1, words. And so that's pretty easy. The derivative of this with respect to pj, right? It's just d of x by dx sort of thing, right? That's just 1, ln of j plus 1. So it's not so horrible. So all of the sum goes away. You're only picking out that one thing. So we just did n derivatives at the same time because j is arbitrary. Yeah, so let's see. So this sum should be still here. So this operator is going to come in. Let's say it's del p7. The p1 term just gets crunched. because they're independent, right? There's a constraint, they sum up. But P1 and P2 and P3, nothing to do with P7. So they all go to 0. So it's like having del y of x plus y plus z. Partial derivative of x with respect to y is, yeah, so 0 plus 1 plus 0. So they're gone. You're only left with one thing, so that sum disappears. You only end up with the jth term. You will do this. It's going to be okay. All right. We talked about partial derivatives. Let's have cookies. Let's have cookies. Can I give you these cookies? It's okay. It's okay. It's okay. Let's ease it up with some cookies. Temporary fix. You don't have to eat them, of course. You can do whatever you want. But you should definitely bring water and chocolate. That basically keeps people alive. Yep. Caffeine, I should say. Okay, actually it's going to be assignment 4. Good times? No, it's just hanging out today. Actually, it has a special place in my little kit that I made. It lives in here. Yeah. There's a Dalek slot, yeah. Cute but evil, kind of like cats, actually. Yeah, right. All right. Okay, let's talk some more things. We're through this bit of, it will come back. It will come back. It's going to be okay. Okay, some minor suffering, and you'll get to this, rather oddly. You'll get to the probability of J. Let's see what, you're going to get to this. And this is some big constant. It has whatever the values of information squared is here, and the cost. G was that constant. Lambda is from the Lagrange multipliers. It's just some number, right? So this is some blob here. You get to play with this a little bit later on. And you get J plus 1 minus some power. So that is, right, the promised land of the power law size distribution. Yep. So that plus 1 kind of matters. Here it is. Here it is again. That plus 1 is here. And we have to figure out what this is. It's not entirely obvious what that is. So power law appears. We have an exponent. This is actually yes, this is a Zipf law story, right? Because it's P of J and they're ordered. They're rank ordered. P1, P2, P3, P4. They're the sizes of them, which you just did in your last assignment, right? P1 is the normalized frequency of the first word and so on. So it is Zipf, and that's why it's an alpha. Zipf's law, we write an alpha. So J is really rank, actually. Okay, and then you can actually figure, you can sort this out. You can actually get this ratio. You don't find out what H is or C is, but you can get that. You can get that. You can also show that this is a 1 along the way, that this part is really 1. And that's, okay, so that's the thing. You show that this thing is 1. So Pj is actually just this term, not just proportional. It's actually this term. And they have to sum up to 1. So always with Lagrange multipliers at the end, you have to use your constraint somewhere. Maybe a couple of times. It's always a bit of a funny business, but you have to use your constraint. Okay, so I'm telling you you'll get to this. There'll be something that you can't figure out, but you know this form is exactly right based on what you've done. And then you say, well, that thing has to sum up to 1. So we're going to do it. We'll sum it up to 1, J plus 1, whatever this is. It's minus alpha. We're just going to call it alpha at this point. We'll give up on finding out what they are exactly. Can't do it. So large, let's imagine n is large. Then we're in the math people get excited, right? Because this is the zeta function, which no one understands, right? So this is the zeta function, and it's where it equals 2. You don't have to worry about it being the zeta function, but that's kind of true. Let's see, why is it 2? Because we've got the sum from j equals 1 to n of j plus I keep saying it, j plus 1 minus alpha, which is, so that means we've got 2 to the minus alpha plus 3 to the minus alpha plus da-da-da. And the zeta function is defined as zeta of x equals the sum from I equals 1 to infinity of I to the minus x. And it has magical things inside it, like the prime numbers, the zeros for the zeta function are along the real part equals a half. I mean, it's just nuts. It's just nuts. Okay. Anyway, but it is that thing. Of course, it has to go to infinity. So if n goes to infinity, this looks a lot like this, except this is starting at 1, right? So this is 1 plus 2 to the minus alpha plus da-da-da-da. So we need to add a 1 to it to get a zeta function. And if we did that, we'd add a 1 to this side as well. So then we get zeta function of whatever that alpha thing is equals 2. And math things like the evil Wolfram thing and various other things have zeta. You can ask them what zeta function of some number is, and you can invert it and so on. So we can just figure that out, right? Zeta function, where does it equal to? Well, 1.73 for alpha, which is a bit high. So if you remember, it's a bit funny. So gamma, in principle, can be between 1 and infinity, right? Steeper this way. The corresponding thing for the Zipf exponent is, let me get that right. Help me with this one. This should be 1 plus 1 over alpha equals this, doesn't it? Gamma minus 1. That's not right. Gamma equals this. Why have I got this wrong? I want to say what's the connection? It's fallen in my head. So let me get this right. So alpha equals 1 corresponds to gamma equals 2. Yes, right? And in general, we expect alpha to be less than 1. Right? It's going to go the opposite way to gamma. It's actually going to have a wider distribution. So this is not 1, which is the famous Zipf exponent. It's 1.73, roughly, for that. So that's a bit of a sketchy bit. And what happens is, this is the Mandelbrot approach, is, well, let's make it j plus a. We'll just make that plus a, and we can play around with that a. So that's a thing to think about in the problem set, is what happens as we mess around with that cost. So it's basically you mess around with the cost function. Instead of the cost being log of j plus 1, it's log of j plus a. And that allows you to dial this, you get a lower value of alpha, one that's closer to 1. But alpha is really always less than 1, so it's not great. Yep. All right. So we get a power law, but we don't quite get the right exponent, and we can fudge it, we can mess around with it a little bit, but we still don't quite get the right side of things. But it remains an appealing thing. You can imagine there are some changes to it that do get us to an optimal story. Okay. So that's the summary for this. It's a reasonable thing to have done. Optimization is certainly, at work. And, in some way, right? But it's difficult because you're fighting against how much things cost. You have to have some level of robustness, which evolution is going to favor, right? So it's not going to be spectacular. So there are some drawbacks to what Mandelbrot has. And the exponent ultimately depends too much on that cost measure. So there's been work since then, of course, but this is not a bad thing to go through. We go through Lagrange multipliers. We're going to see them again when it comes to robustness for forest fires and all sorts of things. It connects well like that. All right, so how are we doing? There's a little bit here then about some of the stuff that's come after. So I'll tell you about that. That's a postcard for you. supposed to represent optimization. That's kind of tricky, actually. Yeah. So this is from the paper, which is, as I said, I think I've said this. It's in a book, actually. So it's published in a book. So this is a bit long, but basically, Mandelbrot states that the actual direction of evolution is, in fact, for language, is in fact towards fuller and fuller utilization of places. It's a bit funny. We're in fact completely without evidence as the existence of any direction of evolution in language. It's a pretty strong statement, right? And then goes axiomatic that we shall remain so. People would deny a direction of evolution could be theoretically possible. Thus, for language, it was kind of I don't know what you would have thought, what you should have thought at that time. Thus, these are little things that are added to the paper, right? So he writes the paper, and then someone comes along and says, "Oh, by the way, you can put your comments in there," and he gets a rejoinder. But I thought this was kind of remarkably strong. You know, the view that language develops in what is essentially a purely random manner. Madness. Mandelbrot actually, who famously could really go at it, didn't really light this guy up. But fundamental linguistic units being the least possible differences between pairs of utterances is a logical consequence of the fact that 2 is the least integer greater than 1. There's a few things like that. All right. Okay. Mandelbrot. Great. All right. So we'll get to some of this later on, soon. So people have played around with random growth kind of things and adding optimization. A couple of examples. So we'll talk about this. This is very famous work. Great acronym, HOT, right? Very well played. Highly optimized tolerance. And so it's a beautiful story, and they kind of try to get both evolved systems and engineered systems, ones that are sufficiently engineered, complex kinds of systems, to show that putting in a robust, like trying to make them resilient, you do a pretty good job, but you end up with power law size distributions of failures, right? So most of the time, and they're the power law size distributions where most of the time things are small. So most of the time you have little forest fires, not so bad, but you've set up the whole system through fire breaks, say, such that, because there's cost, right? There's cost to maintaining fire breaks, right? That's the problem. So you're gonna let that whole area out there go. That's okay, because there's never any lightning. But of course then there's boom, and it all goes. So you get, that's the idea of that. So they have a story that these power law size distributions can appear over and over in systems as a result of an attempt to make them safe. This is 2002, right? I mean, this is kind of amazing. I mean, we have physicists here. This is Raisa de Souza, and who are new at MIT, talking about ways to get scale-free networks and so on. All right, so this is still the same idea that it's kind of some blend. This is funny. So there was after all, I guess Simon and Mandelbrot are still arguing with themselves. That hasn't played out yet. But this is a big thing to point out, that Miller, this is a fellow Miller who was at Harvard as well, as a psychologist, I think is famous for a number of things. One is that we can only remember about 10 digits, 10 numbers, based on some studies, of course, of Psych 101 students. Anyway, but people really, that's one of those things they repeat. It's like, drink 8 glasses of water a day, sort of thing. It's like this. This is a truth of humans. Total malarkey. Okay, so Miller appears, and then this is rather rude, but writes an introduction to a reproduction of Zipf's, one of his books, which is a psychobiology of language. It's a crazy title. It's a 1935 book, actually. And then, so Miller's a little rude, actually. So let me see if I can get some of these. Actually, some interesting thing, talks about the genes of language. And just to say this, you'll see this is 2010, right? Random texts do not exhibit real Zipf's law-like rank distributions, right? What Miller will say here, and what a lot of people will repeat, is that if you randomly type, so if the analogy they use is monkeys, you randomly type, and of course you'll hit a space bar now and then, you just randomly type, you will produce something that has a Zipf's law distribution. And you will get some kind of power law distribution, but it'll be clumped like this. It won't look like a nice smooth power law distribution. It'll be kind of clumped like this in log space. And rather obviously language doesn't look like that. So So it's a bit funny. This happens a lot. It's like, oh, I've made something that kind of looks like your thing statistically using this, silly method. Therefore, it's meaningless, or it happens for free. But they're not getting at the mechanism at all. They've found another mechanism which just isn't there. There are many ways to get to these power law distributions. Let me read out some of his stuff. It's kind of fun. Fun. Miller. Can I get to those? Oh, I don't think I can. Basically he says, you can zoom in on those, that if you like Shakespeare and stuff, do not read Zipf, right? He's a butcher. He hacks language up. He does horrible things to it. He doesn't care about words. And then anyway, it's all just monkeys randomly typing. So basically it just says, it's not very interesting. Anyway, here's his book, read it. So it's kind of nasty. Let's see. I don't think we need to talk about Krugman anymore. This is all extras. Okay, all right, good. So here's a nice study. So this is 2008. I mean, this is a long time after the whole Mandelbrot and Simon business. And it's looking, and I mentioned this as sort of a prelude before, it's Debian Linux distribution, which were named after characters from Toy Story. Woody, Sarge, Etch. Right, so they release a new distribution. It's bigger, there are more packages, and the packages point to each other. They have dependencies, which is this horrible business of, you have to install this package and then this one, and then if you were smart enough, you could do it, and then eventually package managers got to be a bit better, but sometimes they exploded on you and said you don't have this, and you're like, yes, I do. Or it needs this package, it needs a more advanced one or an older one, or crazy. Okay. All right, so this was one way. This comes out of Didier Sornet's group, and I mentioned one of his books, an overview. This guy was a student in one of the courses I taught at the Santa Fe Institute for a year, 2010 perhaps. Anyway, so this is what is this? So this is a PDF. This is the number of links coming into packages. Right, so it's got a nice parallel size distribution. And you can see the sort of horribleness in this next bit here, which is you want to see if this rich gets richer mechanism is there. So you can look at the history. They have 4 snapshots in this case. Here's the system, and here it is, a year later or whatever it is, or 6 months later and so on. So they're snapshots. So you're not really seeing that detail of, this package now has a link to this package, and then now it has a link to, you're not seeing all of that growth. But the idea is that, roughly speaking, so if a package has this many links coming in, this is its change, right, over time. So it's pretty scattered. It's on a log scale, but it's not bad, right? So there's this basically kind of linear growth. So it's a rich gets richer story, seems to be holding. But it is hard. This is just one. It's a gigantic thing. A Linux distribution is a gigantic thing. There's a lot of data there, but it's still not, enough to show a perfectly clean thing. But it's pretty good. So it does seem that where we can get our hands on things, and there's another example. This is actually from 2001. This is coming after the Barabazi work, which we'll talk about in complex networks, a big deal, the scale-free network stuff. This was a small paper that appeared in Physical Review saying, well, let's just take Simon's model for the web. This web thing, which at this point is 9 years old. They probably did this work on data from 1996 or 7. My website is from 1995. That's when it started. Anyway, that's pretty bad. So they showed that Simon's model fared pretty well because, again, they could say, well, here's a probability that a new page appears. It was for I think the analysis for the Notre Dame website, right? So you have pages, they're pointing to each other, and a new page could appear. Okay, actually, and they also did this. Alta Vista, this is hilarious. Have you heard of? You've heard of it, right? So back in the day, Alta Vista, Excite. What are the others? Can you remember any others? Ask Jeeves was a different kind of thing. Yahoo had its own search thing, which was human curated. It was different, yeah. Yahoo, what a terrible company. Oh my God. Which one? Gopher, I don't know Gopher. They got crushed by Google. I mean, that was the thing. They got crushed by Google because Google just said, it's based on links. We'll talk about it later on. And everything else was, you know, you put fish in as much as you want into your metadata, and it will say, oh, this is about fish. But yeah, the Google thing works on social stories. All right. Here's what I was trying to do before. What was I doing? Okay. So, so the exponent that you would get out is 1 plus 1 over 1 minus rho. This is the Simon derivation. And for 0.01, right? Sorry, it's 0.1. Yeah, so this is going to be roughly 1 plus 0.1 if you do the little Taylor expansion. So it's roughly 2.1. And that's what you roughly see for this thing. It turns out that in general, and we've talked about this, the in-link and the out-link distributions are a bit different. It's okay. But not bad. And then direct measures at the time, 2.1, 2.09. So that's not bad. So it seemed to conform. There you are doing, you're just measuring this thing like viscosity or whatever it is, or in this case it's innovation rate. You're not quite showing the whole pattern. I probably should reorder these things. But you're showing that the model at least holds up formula-wise, whereas this previous stuff did a pretty good job of showing that in a detailed way, it's really a rich gets richer kind of mechanism. So that's pretty good. I think, here's our nutshell. Right, so Simon seems to work basically. It's a rich gets richer thing. I wanted to say, I guess, with the citation thing, is he is in the rich gets richer game as well, right? I mean, his papers are, they're very much in that thing. They're snowballing away. You see, Mandelbrot gets out of power law from this kind of somewhat crude argument about optimization. It's not perfect, but it seems like you almost get that somewhat for free, right? So this way it's balanced. It fits with Zipf's old story that you have tools, language is made out of tools, and that it's useful to have some things that do lots of things for you, hammers and screwdrivers and so on, and now and then you need a specialty object to do something. All right, so evolution of tools would be really interesting too. I mean, think about bike tools, right? That they've really changed, and we've figured out, let's make everything just work with an Allen key. I mean, it used to be you have all these exotic tools for different pieces. That would be interesting. Okay, so that's good. You can leave. We're good. The next assignment's round. This is a baby robin. We have one birder, so I'm going to do this. We had a pet robin. This is the feel better thing at the end. Fell out of a tree last year and was just complete. We thought it would be toast, right? So we had to bring it inside because cats would eat it. Named Tsubasa, which is Japanese for wing. My daughter named it this. Anyway, very friendly, and the mum and dad would come and feed it every day. So we'd put it out in the back, and they'd come and feed it. And then we have to take it inside because look at this, and that's just food. That's just cat food. Anyway, it's pretty great. We had a lot of good fun with this thing. The addendum to this is that chipmunks are evil, evil, evil little things. Because I saw one attack this guy, just like hiding there, and I'm like, oh, this is so cute. There's a chipmunk and a robin. And then it went, yeah, and it went, boom. And there's a psychotic look in his eyes, and it turns out that chipmunks will attack and they will eat baby birds. Squirrels rule. Okay, so good to know. No one knows this about chipmunks. They've pulled the wool over our eyes. Thank you. Good. Simons, yes.